Hello, science students. Today's lesson is about momentum and Newton's third law of motion. Let's begin by reviewing Newton's first law of motion. It's also called the law of inertia, and it says that an object at rest will remain at rest, and an object in motion will remain in motion at a constant speed unless acted upon by an unbalanced force. In the simplest terms, it's basically saying that it takes a force to move something or to change the way something's moving. So, forces cause motion. Remember, we defined a force as a push or a pull acting on an object, and motion is the change in its position. Inertia was that idea of that all matter has a tendency to do nothing or remain unchanged. It doesn't want to start moving unless that force pushes on it. Same type of thing, it doesn't want to stop moving unless it has a force act on it. Newton's second law of motion described exactly how to calculate the size of a force. And it said that the net force of an object is equal to the product of its mass and acceleration, or basically that force is equal to mass times acceleration. Acceleration was another one of those key vocabulary terms. And it's the change in the velocity of an object. And you can kind of think about velocity as like speed, but it also includes the direction that it's going. Newton's second law, you have to measure the mass and acceleration. Objects accelerate when their velocity changes, so either they speed up or slow down, or then their direction changes, so it starts to change its path. Any of those would be an acceleration. Let's look at this example. You've got a car that starts out moving at 0 meters per second and accelerates for 2 seconds to 10 meters per second. Its acceleration was 5 meters per second squared, and with a 25 kilogram mass, that calculates out to a force of 125 newtons. It took 125 newtons of force to move that car from a standstill to 10 meters per second. But now, what about if that object is moving along? It has a constant speed, but it's not increasing its speed. That velocity doesn't change. So the object's not accelerating. The speed didn't change. Does this mean that the object doesn't have a force behind it? Well, by the definition of a force, no. There was no force acting on this object. Here, if you start out moving 10 meters per second, you drive along for 30 minutes at that same speed. There's no acceleration. That speed stayed the same, and so no force was applied to the car. But the car has some force. It has something you might think of as a little oomph. If you got hit by that car, it'd still sting a little bit. We call that the car's momentum. Momentum is the product of its mass and velocity. Velocity is speed and direction. In this example, it's a very similar equation to force, but momentum is P equals mv. I don't know why they chose the letter P, but I do know that the letter M for momentum, of course, was already used for mass. You can think about momentum as if it was the amount of motion an object has, or kind of like the amount of force it's going to take to stop the object. Let's look at this. The car has momentum. It takes a force to change that object's momentum. This brings us to our third law of motion. Every action, there is an equal and opposite reaction. Forces occur in pairs. This may seem a little confusing. Let's take a look at a couple of examples. Here in this first example, you've got a person who's riding a skateboard. They push on the ground with a force. Their foot pushes on the ground with a force. But the ground pushes right back on that foot with an equal and opposite force. And that's what causes the skateboard to move. Since those forces are equal, remember F equals ma, so the same force for the ground and the same force on the foot. Since the ground's much more massive, that person and that skateboard are going to accelerate. The Earth accelerates just a tiniest little bit, but nothing that we can perceive, nothing that we can see from where we're at. Another example. Here you've got someone who's stepping off of a boat. They have an action where they push off on the boat. That applies a force there to the right. That boat pushes off of the person and applies a force to the left. In this instance, the boat and the person are roughly the same mass, roughly the same size. And in this instance, both the boat and the person end up moving a little bit. And that person may not actually get far enough as it's pushing off of the boat to end up on the dock safely. They may end up wet. A third example involves a balloon. That balloon, there's an action where the balloon pushes the air out through the opening, and there's a reaction where the air pushes back on the balloon, and that causes the balloon's motion to go flying to the right. Remember that when forces are balanced, an object is stationary. Only when those forces become unbalanced does the object move. It takes a force to make an object move, accelerate, or to stop its motion. And objects that are moving at a constant speed have momentum. Motion is a form of energy. Moving objects have energy. Our law of conservation of energy says that energy cannot be destroyed, but can change forms or be transferred. So I want you to start to think about what might happen when two objects collide. What does that force of a moving object do on the thing that it runs into? Does that force get transferred into the other object? What happens to the object that was moving? How does its motion change? Lucky for us, by understanding Newton's 3 laws of motion, the idea of forces and momentum, we can understand how two different objects will act and react when they collide. Thank you and have a wonderful day.